Welcome to this EU Green Week partner event entitled European Hydropower is Important for the Green Deal. My name is Bjarne Børresen and I'm Work Package Leader for Communication, Dissemination and Exploitation for the Hydroflex Horizon 2020 project. In this short hour, we will highlight different aspects of European hydropower. And without any further ado, I'll give the word to Eivind Steen from Eurelectric, who will give us some brief facts about European hydropower.
Hello, thank you very much for the invitation to speak at your event. It's a very timely and important event now that we are preparing for a big legislative package coming in, and the climate law being recently decided. So there's an exciting time for renewable energies. So I was asked to talk about a little bit of facts of the numbers of hydropower in Europe, and within 5 minutes, that is, there's a lot of numbers that we can bring up, but I've made a short selection. So basically, what makes hydropower so unique? It's often forgotten, probably not by the participant here, but a large chunk of the renewable electricity in Europe is hydropower, actually 40%. And 97% of electricity storage in the EU is also hydropower. And that is about the quantity, but then of course the quality is that we know that the qualities of hydropower is important. It offers flexibility and storage at any moment. This will of course be brought up today in the session. But just one last point is that the more renewable energy we have, the higher the value of hydropower is in the system. So that's an important thing to bring to the table. So when we go into the numbers, you could sort of say we have, of course, hydropower facilities for different needs, and we roughly, or at least in our case in the Eurelectric world, we roughly divided into two, sort of renewable generation and renewable flexibility. And under there we have run-of-river, reservoir storage, and pump storage. So if we look at the generation capacity the capacity of run-of-river and reservoir in Europe, you have 105 gigawatts. But if you bring in Norway, Iceland, Turkey, UK, and Switzerland, the numbers are obviously higher. We are about 180. And when we're looking at the generation of run-of-river and reservoir, we are at 344 in EU 27. But when we bring out these countries that I already mentioned, we are almost at 600 terawatt hours. And then we look at the last sort of pure pumped storage. We have a capacity of 46 gigawatts in EU 27. That goes up to 51 if we include these other countries. And also the generation capacity is at 26 terawatt hours, but at with this larger scope with these other countries, you're at 31 terawatt hours. So these numbers are 2018 numbers. So of course, these are moving quickly. It's already 3 or 2.5 years, we could say. In 2018 there were 1,005 terawatt hours of renewable electricity in total in the EU. I don't have a recent number there, but that is for sure a lot higher today. But if we put this into context, as I mentioned quickly, is that we are in a situation where now the EU has increased its its climate target. That means that you need to have even more renewable power generation. So if European Union is to reach their goal of 55%, you will need to have up to 67% power generation to be covered by renewables. And wind will have to double, and solar would have to triple. But what is kind of interesting from the impact assessment from the European Commission is that they are also looking at an increase in generation for hydropower generation of about 10%, and capacity increased capacity of 40% for pumped hydro. So the Commission itself is looking at an increase of hydropower overall. So with that, I think I'm not going to go into more details. We're at the end, and I'm looking forward to hearing the other participants. Thank you very much.
Thank you, Eivind. Hydropower has a long history in Europe and is tightly developed with industrial development in many communities. One such place is Tyssedal in Norway. And I'm glad to give the word to Knut Markhus, Director of the Norwegian Museum of Hydropower.
Thank you very much for the invitation. As it was said, I work in the Norwegian Museum of Hydropower and Industry, called Kraftmuseet in Norwegian. The listed Tyssedal power plant is our main arena. On this picture you see the power station from 1908, beautifully located by the Hardangerfjord. You find us here in the western part of Norway. The power plant is situated in Tyssedal, a small industrial village close to the small town Odda. This part of Norway is ideal for the use of hydropower, and Norway has taken advantage of that. It is many power plants in the west of Norway, where you have access to the sea, the connection to the rest of the world. If we move back to the end of the 19th century, this were small farming villages. Odda had quite a lot of tourism, with many hotels rising, but no industry really. Tyssedal had only 2 farms with around 30 inhabitants, so it was a quiet place. In the dramatic nature surrounding Odda and Tyssedal, the waterfalls and wild rivers were numerous, and the main attractions in the growing tourism. Some small mills used the running water, but the main use of the waterfalls, if you think business, was the magnetic power they had as tourist attractions. Many areas in Europe had come further than Norway in the development of industry. Anyway, this part of Norway, and here we are in Ironbridge in the west of England, the Ironbridge Gorge, crowned as the birthplace of the Industrial Revolution in the 18th century. Water power played an important role in the early stages of industrialization. The Industrial Revolution is most often associated with steam power and coal, but in fact it was water power that was the driving force behind the earliest stages of industrialization in Britain. The hydropower as we know it today, with hydraulic turbines, was developed in the late 19th century, and for this technology the Norwegian landscapes were perfect, especially the areas in the western part with a lot of rain and snow, wide lakes in the high and steep mountains. It was good conditions for introducing the hydropower technology and built power plants. Around 1900 it was a rush in Norway for acquire ownership to the water resources. Unlike many countries in Europe, most of these resources were privately owned by local farmers, and many of these were tricked into selling for a very cheap price. The speculators made a big profit when they sold on to the industrial companies. Sometimes the speculator and the industrial pioneer was the same person, like Samuel Eide on this picture, a Norwegian engineer who started buying waterfalls and watercourses around 1900, and also became a very strong industrial leader, and the person behind several hydropower projects in Norway. In the winter of 1906, some international industrial leaders meet in Paris, and Sam Eide was one of them. And the key theme is where can we establish a factory for production of calcium carbide? Another Norwegian speculator appears. He has the watercourses in Tyssedal on hand and argues that Odda is an ideal place to establish a carbide factory, and the nearby Tyssedal perfect for a hydropower plant. And a great advantage is the fact that these places are located by the fjord with a sea route to the international markets. The group decide to go for this, and deals are made. And just a few months later, the construction work starts in Tyssedal and Odda. Sam Eide is the general director for the hydropower company. Two big factories in Odda are planned and built by the Albi United Carbide factories and the Northwestern Cyanamide company. Albi to produce calcium carbide, and Northwestern to produce calcium cyanamide, and these two were linked together. Both of the companies had their headquarters in London, and this is an important thing. Many of the industrial establishments in Norway in this period have a foreign ownership, mainly Swedish, French and British. And in less than 2 years, very quick, the hydropower plant was established, and the factories as well. And this was typical of the time, that factory and power station were built at the same time and close to each other, because the power was local. There was no system to transport it. The completion of the construction in Odda and Tyssedal was quite impressive. The hydropower plant was the largest high-pressure power plant in Northern Europe, and the construction of the carbide and cyanamide plant was one of the largest undertakings of its kind in the world at the time. Rapidly, Tyssedal and Odda developed from a farming district to modern industrial communities, complete with housing developments, schools and social services. In just a few years, the population in Tyssedal rose from 30 persons to more than 1,000. The development of the hydropower plant and the industry continued the next years and the next decades. The huge Ringedal Dam was finished in 1918. A new power plant, Tyssedal 2, was finished in the same area in 1967, and now the power production in Tyssedal became a part of the national interconnection hydropower network. When we come to 1980, the new power plant Oxla was placed inside the Tyssedal mountain. The old power plant that started its production in 1908 was then closed down in the late 1980s. In 2000, this was listed by the Directorate for Cultural Heritage and went through a comprehensive restoration project for 5-6 years, and now it's a part of our museum and telling this story. We are still a municipality, hydropower municipality. Here you see the zinc factory in on the picture in Odda, and Tyssedal behind. It's a heavy industry as the main business in this place. And Norway is a hydropower country. The Norwegian power system is largely based on the hydropower. Around 95% of our electricity production comes from these resources. This is also, next to oil and gas technology, one of the few areas where Norway is among the technological leaders in the world. And this is an important aspect with the hydropower development in Norway. From the start, around 1900 and the next decades, hydropower development built a knowledge and competence that became important in other areas as well. The expertise was transferable and useful when Norway started with oil extraction around 1970, and we can draw a line to the development of wind power today. The state-owned hydropower company Statkraft is a driving force in the wind power development. Another important issue in the hydropower development is the politics around ownership of the water resources. As I mentioned, international capital was crucial in the beginning, with ownership in the hydropower plants. This was seen as a scary situation among the politicians. Norway had got its independence in 1905, and losing the ownership to our national resources could be a threat to this independence, and Norway could suffer economically. In kind of a hurry, laws to ensure Norwegian ownership were introduced. First, the so-called Panic Law in 1906, which strongly regulated access to the acquisition of watercourses in Norway. The government introduced over the next years a system of licenses, in which licenses for power development and production were limited in time. After a certain period, usually between 60 and 80 years, the ownership shall be transferred to the Norwegian state. And this system of licenses also became the basis for other national resources in Norway, like the oil resources. Today, the public sector in Norway owns about 90% of the production capacity for electric power through the state, the county level, and the municipalities. So today, the Norwegian power system is largely based on hydropower. It's a success story, not at least when you take into account that we talk about a renewable energy. Hydropower is a part of the solution in the task to reach the sustainability goals. But the hydropower history in Norway is also a story full of conflicts, for there are, of course, downsides to hydropower production. There can be great damage to ecosystems and land areas around a dam. It's areas lost for farmers and indigenous peoples. It's tourist attractions lost when a waterfall is taken away. Untouched nature is no longer untouched. And this conflict between the protection of nature and the exploitation of nature is a main theme in our museum. Hydropower is a renewable energy, but also this has its cost for nature and for people. Well, back to Iron Bridge. I have not elaborated the importance of hydropower in European history. I guess the Tyssedal case and Norway is special. Hydropower is crucial in building the Norwegian industry and building the modern Norwegian society. To some degree, hydropower has played an important role in the European industrial history in general, but with very different direct impact from country to country. It's interesting to compare Switzerland and Norway. It's many similarities. It's a parallel development of tourism before the hydropower era, and then we follow each other in the adventure of hydropower, including quite similar politics for ownership. Our neighbors Sweden has a quite different story, but also there the importance of hydropower in their industrial history is big. If we look to the future then, and also a museum looks to the future. That's exciting, of course, when it comes to hydropower. Maybe and probably hydropower will play a more prominent role in the energy production in the next decades in Europe and many parts of the world, as a very steady companion to other renewable energy sources. The fossil energy production should end more or less, while the hydropower should expand. And this last picture is where you can look into the future from Trolltunga, the Troll's Tongue, looking over the Ringedal Dam in Tyssedal, and all this is a hydropower landscape. And I will say welcome to you. You should come here and visit at some point. Thank you.
Thank you very much, Knut. Rivers and water resources may have many uses, and there may sometimes be conflicts between hydropower development and other usages. This is a topic of active research and I'm happy to give the word to Terese Venus from Technical University of Munich in Germany.
All right, so today I'm speaking about challenges and perceptions of hydropower in the environment. And this is a study based on a public acceptance survey we conducted within the EU Fit Hydro project. A bit of background, as you heard, run-of-the-river plants have a significant generation and capacity across Europe, and they also have the perception that they are less environmentally damaging. But at the same time, when there's many plants along the same river, it's difficult to balance conflicting local interests and values related to water use, recreation, biodiversity, nature conservation, fish protection, and land use. Thus, within our study, we compared public perceptions from local residents of run-of-the-river hydropower in their communities across Europe. So against this background, it's important to remember that there's many environmental challenges associated with hydropower, including flow release, habitat adjustments, fish migration, both upstream and downstream, and sediment management. But at the same time, there's many potential environmental mitigation strategies for all of these challenges. And so the goal of our study was to understand what perceptions are from locals of these hydropower, and also understand how to design better mitigation strategies to account for these beliefs. So in our study, we focused on case studies across hydropower-rich regions in Europe, within the Alpine region in Germany, within Iberia and Portugal, in Sweden and Scandinavia, and France within the France-Belgium area. And each of these case studies, we picked one main hydropower plant and an area city nearby where we conducted the surveys, and these were selected based on specific criteria. So each of the case studies within the region needed to be in a hydropower-rich area, characterized by a, particularly in the close area, vicinity, and a number of run-of-the-river hydropower plants with smaller capacities. And they should also have an ecological measure in place. So we posed the question, what do locals think about hydropower in their region? And we structured public acceptance factors according to the following categories. We thought about economic costs and benefits. This has to do with economic development, job creation, effects on other industries, tourism, fishing, as well as energy security. We also considered how hydropower may affect the quality of life in the area. How does it affect landscape aesthetics, health and safety issues, flood protection? And of course, we considered how it affects ecosystems. And this encompasses both the natural flow of the river, but also effects on habitat and biodiversity, fish populations. We also considered to what extent people and locals are allowed to be involved in to publicly participate and be involved in decision-making processes. So this encompasses whether they're part of the planning and decision-making process or not at all. And we also considered energy policy, which encompasses any economic support, such as subsidies or feed-in tariffs, as well as support related to profit sharing. And we also considered energy preferences in general, so how they related hydropower to other types of renewable energies, and also what they felt was important in terms of flexibility and energy storage. So based on these different factors, we asked locals what they believed. And within the survey, we used a mixed method survey called the Q methodology, and we gathered statements related to these categories, and we asked locals, as shown here, to sort them into a grid based on how much they agree with the statement and disagree with the statement. And through this survey, we were able to identify major themes across the 4 regions and see where there was controversy and consensus and similar problems or good conditions across the 4 regions. In our analysis of around 250 participants, we identified 4 perspectives about run-of-the-river hydropower. in our first perspective, this represents maintaining regional control. As we heard, there's strong opinions about how people view ownership of hydropower and how it should be managed. So this factor was present in all of the 4 regions, and it was important to understand who owned and who had access to hydropower as a resource. The second factor was perspective was related to fighting climate change, and this perspective, or people that loaded significantly on this factor, were concerned with hydropower's contribution to a renewable energy transition and any potential flexibility or energy storage it could provide. Perspective 3 was focused on protecting natural ecosystems and supporting biodiversity and promoting fish protection and fish populations. And the fourth factor was focused on promoting citizen well-being, and this encompassed anything that could affect local citizens, including flood protection, but also recreational opportunities. So across the 4 case study regions, the first 3 perspectives were present across all of them, in all of them, but the fourth factor about promoting citizen well-being was unique to Portugal. And we think that's because in our case study regions, Portugal had experienced significant flooding in the past years, and it was thus a more salient point for locals there compared to the other countries of Germany, Sweden, and France. But what we see here is that what emerges as most important across these regions is both ownership and the protection of natural ecosystems and climate change. And in our analysis of controversy and consensus, we could see which points or which topics were most controversial and which were most had the greatest consensus. So on the y-axis, we see statements. These relate to each of the ideas or the opinion statements about the main factors for public acceptance. And on the x-axis, we see the scores. And a positive score indicates that the group agrees with it, and a negative score indicates that they disagree. So at the bottom of the table, at the figure, we see that these are the statements that are most agreed upon, and at the top is the most controversial. So to take an example, the one at the bottom, one of the most controversial statements is existing hydropower plants should one of the greatest consensus statements is that existing hydropower plants should be modernized before new ones are built. So there was a strong agreement across the regions that it was important to stress and support modernization. On the other end of the spectrum, one of the most controversial statements was related to free-flowing rivers and the idea that rivers are meant to flow freely. So here we saw a strong disagreement, particularly between the perspective 4 related to promoting citizen well-being, who disagree that rivers are meant to flow freely, and factor 3, which is focused on promoting natural ecosystems, that believes it's very important to promote the free flow of rivers, or as much as possible. And in our analysis, when we conducted the survey, we also asked them why the participants rated that or sorted them in this way. And one of the explanations related to free-flowing rivers is that hydropower should be limited as much as possible to particular river stretches or certain rivers to allow as many rivers as possible to freely flow. But of course, it's an interesting question to consider what is meant by free flowing and what is even the natural flow of a river after such a long history of hydropower development. So the key takeaways from our surveys across these 4 regions was that controversy, a major theme of controversy was plant ownership. It was unclear whether it should be state-owned or privately owned, and there was certainly strong opinions about whether foreign companies should be allowed to own hydropower in each of these countries. But there was significant consensus across the regions about the importance of modernizing and supporting modernization of hydropower, as well as supporting ecological measures, both in the form of fish protection and flow measures. So one of the main takeaways from our research or recommendations is that monitoring is extremely important, and communication. And we came to this conclusion because one of the main issues with ecological measures in these specific case studies was that there was quite a lot of confusion about how the measures worked themselves and whether they were working at all. So if they are working and there's monitoring being conducted, it's important to communicate those results to the public and explain. If you're interested in more about this research, I refer you to our publication in Energy Policy. And finally, this is again research conducted within the Fit Hydro EU project. Thank you.
Thank you, Terese. The title for today's event is European Hydropower is important for the Green Deal. Why do we make this claim? To help to clarify this, I'm happy to welcome Fredrik Engström from Vattenfall, Sweden.
Yes, hello everybody.
Fredrik, can you explain a bit which role hydropower has today in the Swedish power system and how it interacts with other renewable energy sources?
So in Sweden and also in the Nordic region, in the synchronous system, hydropower has always been the big flexibility resource based on those big reservoirs that we have, that huge storage that is so unique for the Nordic region. Still today, the big flexibility is actually balancing the day and night shift in demand. But quite fast, increasingly now, we see that also harnessing the differences in hydropower, in wind power production will also be more and more important, and we start to see that quite pronounced now in the Nordic system as well. So when wind power is producing a lot in the Nordic region, hydropower needs to step back and steps back and awaits sort of when the wind power production goes down. So this is sort of an added-on flexibility that is now being required. And here the big storages in our reservoir is actually well suited to promote this, since typical wind power patterns are on the order of days rather than just few hours. Also, traditionally in the Nordic system, hydropower has been the sole supplier of ancillary services, and that's sort of another part of the flexibility spectrum to be able to also support the frequency and related services as almost right now the only production source that does that.
Just to clarify, Fredrik, and we use this term ancillary services. So for people who are not maybe working in the power sector directly, can you explain what are these ancillary services and maybe why are we so focused on this balancing?
Good point. So ancillary services, that's something on top of the energy production that, for instance, hydropower will supply to the system. Because we also need a power system in balance. For every second, we need the demand and the production to be in balance to keep the frequency at 50 hertz as we are used to, and sort of is the foundation of our synchronous system. And our hydropower units, they are constantly monitoring this frequency, and if they see that the frequency is dropping below 50 hertz, that means that we have too little production in the system. Then they will automatically start to produce more to support the frequency. And on the other hand, if we see that frequency goes up, we're stepping back production because then we have too much production, and therefore keeping the system stable. And there are also other services that are connected to this, but that is the most important part.
Eivind Steen in the introduction mentioned pumped storage, and I know that Vattenfall also owns and operates a Goldie-style pumped storage plant in Germany. First of all, Fredrik, maybe you can explain what is pumped storage?
Well, in contrast to more conventional hydropower and run-of-river plants basically feed on the water that comes in the river. We also have our reservoir plants with big storages where we can run more flexibly by using that big storage volume in the reservoir upstream. But both of those build on sort of the precipitation coming and being collected in the reservoirs, and then we let that flow downstream in the river through the different power plants. Pump storage, on the other hand, can work in combination with conventional hydropower, but then we also feed water back into the system, and most often to an upper reservoir that is maybe an artificial lake. So we take maybe water from a river, we pump it up a few hundred meters to a small reservoir, and then by then consuming energy. And then when reservoir is full, we can then generate on that water volume that we just pumped up. So there's no net production, but rather quite important and big and dispatchable balancing force or balancing energy in the system, and which can also easily be combined with these services that I mentioned earlier.
And I guess also then these pump storage can help to support, for instance, solar power, so that you can produce the solar power at daytime and then you have the access to your pump storage, or you can produce at nighttime. Is that correct?
Yeah, that's a good example. And typically day-to-day flexibility is what pump storage usually was built for. So obviously when the sun is shining and solar power is at its peak during daytime, we can use that excess energy to pump up water into the upper reservoirs. And then during night when the sun is not shining and solar power is low, we can use that water and then put energy into the system, to thereby supporting sort of the solar energy fluctuations.
There is a lot of buzz around battery technologies. We see a huge increase in electric vehicles, and there's a lot of excitement around battery storage in the power system. Do you think that batteries will replace hydropower in the near future?
I'm quite certain they will not replace hydropower, since it's only storage, it's no net production, but batteries can play an important role in the power system. Especially when it comes to shorter time periods and the really fast frequency responses that we see an increasing demand for in the system, because batteries can be faster even than hydropower. But on the other hand, if we are talking balancing wind power, where we see big volumes of energy during maybe one or a couple of days or maybe more, those energy volumes are so big, so it's not reasonable to capture that with batteries. So I think we're looking at a very important combination here to actually maybe step back a bit with some flexibility in the hydropower when it comes to these really fast services, and replacing those with batteries. But we also need this really big storage. The biggest storage is reservoirs in Sweden, and I think also in Norway. They correspond to hundreds of millions of Tesla Powerwall batteries. So it's you must understand the magnitude of the storage that we have in the Nordic region.
Thank you, Fredrik. This was very clarifying, and thank you very much.
Thank you.
In the last part of this meeting, we'll briefly present 3 European research projects related to hydropower. First, I'm happy to welcome Elena Vagoni from EPFL Switzerland, who will present the Xflex Hydropower project.
Okay. So first of all, thank you very much for the invitation. It's a pleasure to be here today in this European Union Green Week event to present our project, Xflex Hydro, the hydropower extending the power system flexibility project. My name is Elena Vagnoni. I'm a scientist at EPFL in Switzerland. And in particular, within this project, I'm leading the research and the scientific activities of the project. As we saw in the previous presentations, there are ambitious targets by the European Union for the next decades, especially the target of having at least 32% of energy coming from renewables by 2030, and even more ambitious scenario by 2050. In this energy transition, hydropower, we hope that will have a major role in the transition, especially in supporting the needs of the power system. Hydropower has already a key role as it is a renewable energy and it is dispatchable, while for instance wind and solar are not. And so those sources are creating instabilities, unbalancing in the grid that must be. So it's a key factor to have hydropower, increasing first of all the generation of energy, but also the participation to the so-called ancillary services markets that have been previously defined, in order to guarantee a good balancing of the grid in both frequency and voltage. It's within this framework that we are working in our Hydroflex Hydro project in order to increase the flexibility that hydropower can provide to the power system, and also the overall potential of European hydropower fleet in participating to the generation markets. Our project is built upon different phases and it counts on 19 partners. We have research institutions, universities, but also industries, especially equipment manufacturers and utilities. It's an innovation and demonstration project. That means that all the activities that we are developing and for which we are working in our research activities have to be demonstrated on a real full-size power plants. For that, we selected 7 sites, 7 demonstrators that you can see here in the map, where we will demonstrate the hopefully performance that our activities can bring to improve the performance and flexibility of the overall European hydropower fleet. Those demonstrators, those hydropower plants have been selected for being widely covering the almost overall European hydropower fleets. So in terms of types of hydropower plant, we have pump storage, reservoir storage, runoff river power plants, and also a wide range of capacity. We pass from 5 megawatt in Smooth up to more than 1 gigawatt in Grand Maison. And so in this way, we really hope to cover and to address our research activities to cover all different types and characteristics of the power plants in Europe. The project is built upon 4 years, so starting in 2019 and we end in September 2023. It has 3 main phases. The first is the innovation phase, where we deal with the definition of what is flexibility and how hydropower can contribute to the flexibility needs of the power system. The development of a digital tool, the Smart Power Plant Supervisor. I will give you a few more insights on this in the next couple of slides. On a demonstration phase, with the 7 demonstration, where we'll implement all the different activities and targets of innovation part, and we will demonstrate their performance. And finally, a deployment phase, where we will draw a roadmap and write down guidelines based on the results that we achieved during the demonstration phase to guide how to successfully modernize the hydropower fleet to comply with the new flexibility needs of the power system. We will also perform a market analysis and to see the impact of our activities on the market and the dissemination cross-cut of the results we achieved. So just to spend really a couple of words on the Smart Power Plant Supervisor, which is the core of our project. So the Smart Power Plant Supervisor is meant to be a methodology for the optimized integration of flexibility technological solutions. And in particular, what we want to achieve is the integration of turbine dynamics and condition knowledge into advanced control unit. That means so to have a digital knowledge that can be exploited by a control system, for instance. So that's why here on the right of the slide, you have different levels of communication from the energy management system up to the Eurelectric unit, how it is working right now. And typically before our project, so at least up to now, except for a few exceptions, normally we hydropower plants works around one single optimal points. What we are doing with our project is, first of all, to implement and optimize the new flexibility technologies that are already available on the market, namely variable speed, hydraulic short circuit, and hybridization with batteries, depending on the characteristic of the power plants. And we are adding a digital tool, the Smart Power Plant Supervisor, that leverages all the information and the knowledge that we can have from the operation of the power plant and optimize the use of those technologies. And what we want to achieve, so instead of having one single optimal point of operation around which the operator can play, we will have multiple points that take into account several dynamics and not only, for instance, the best efficiency point of the power plants. So that was a really overview of our project. I invite you to visit our website and to keep in touch with our social media that you can find in this slide. And thank you for your attention.
Thank you very much, Selena. The next project, AFC for Hydro, is led from UPC in Spain. I'm happy to welcome Xavier Escalier to present this project.
Thank you very much. Let me share the screen. Okay, so thanks again, and I am very pleased to present the active flow control system for improving hydraulic turbine performance of design operation. Well, it has already been clearly described in the previous presentations that hydropower has a very important role in the energy transition, and in particular, the European Union is looking for three main goals. We want to put energy efficiency first. We want to make Europe a leader in renewables, and we have to achieve a fair deal to consumers. So based on these objectives, it is very clear that hydropower is a very clean and green alternative to fossil fuels, and that permits to generate electricity in a cheap way compared to other non-renewable resources of energy, such as the coal. And moreover, the dams where we have installed the turbines also can provide a means of regulating water flow on the rivers and can be used to benefit the environment. So here you can see an outline of the European Union integrated energy system that is planned to be developed in the next years. We have the consumption from the factories and the cities and the power generation sources. It is clear that we want to reduce the thermal power coming from fossil and nuclear sources by increasing the participation of less predictable generation energy sources, such as the wind and the solar. It is in this sense that hydropower plays a central and complementary role relative to these other renewable energy sources, because, as it has already been clearly explained, it can provide many advantages, such help to regulate the frequency, it has the capacity of storage of energy, and it has many other benefits. Anyway, we have to take into account that the change of the climate conditions is going to affect negatively hydropower. It is clear that we will have to face alterations of the natural waters. For instance, the presence of extreme weather events will alter the river runoff due to the change of precipitation and temperatures, which will pose significant problems for the hydroelectricity generation. Therefore, the conclusion is clear. We need to improve hydropower technology, and this is the main objective of AFC for Hydro project. In particular, this project is focused on the improvement of existing hydraulic turbines of any size and capacity, and the idea is to try to improve their efficiency, to enlarge their operation range, and to ameliorate the performance. For instance, on the right-hand side, you can see a plot where in blue we have what we expect to obtain from the project, which is the efficiency curve of hydraulic turbine for different operating loads. As you can see here, nowadays, around the maximum efficiency point, we can only operate in a narrow range of output loads. And the objective of our project is to try to enlarge this operating range so we can make the turbines work at lower flow rates and at higher flow rates than before. So we are more flexible in terms of generating energy. But the difficulty of trying to achieve this enlarged operating range is that at these conditions we have sometimes unstable pressure pulsations and also, for example, unacceptable cavitation levels that need to be reduced if we want to reach our objective. So that's the idea behind our project. So the conclusion also, if we achieve the expected objectives, is that the impact will be very good for hydropower. With this new technology, this new system, we tend to increase generation flexibility. This will allow a better integration of hydropower in the energy system. If the hydropower performance is increased, we will make also generation costs very low compared to other non-renewable sources. Moreover, we will also be able to reduce the cost of existing units, which will favor the circular economy. And nonetheless, we will be able to reduce the environmental impact by improving the utilization of water through the hydraulic turbines. In summary, the achievement of the objective will increase hydropower competitiveness. How we will do that? So here you can see a description of the concept with some images. So the problem that we have if we want to extend the operation of turbines out of design conditions is that some deleterious and unacceptable flow phenomena occurs, for instance, in the draft tube after the runner, that provoke, as I said, unstable pressure fluctuations and strong vibrations. So our proposal is to develop what we call injection systems, which should be controlled and optimized methods to add energy in the draft tube during operation in order to reduce these negative effects out of design operation. In order to verify that our injection systems, which are called IPM and ICM, corresponding to injection of pulsating momentum and injection of continuous momentum, work well, we will continuously monitor the condition of the machine by means of a structural health monitoring system that will fit a mathematical algorithm inside the controller, and that will decide the best operating injection conditions to be introduced in the machine in order to achieve an optimal hydraulic turbine operation, efficiency, and dynamic behavior. One of the restrictions of this system that we need to obtain is that at the end, this concept should be affordable and suitable to be fitted in already existing hydropower turbines of any size and design. For that, we have already started to prepare a series of tests that will evolve from laboratory experiments in more scientific conditions to more real industrial environments in the case of full-scale prototypes, as we see here in this slide. We will start with laboratory tests at the turbine model test stand located in Alkarlevi laboratory that belongs to the Vattenfall Research and Development Center located in Sweden. Then after these first laboratory experiments where more scientific objectives will be intended to be achieved, we will move to more real applications, as I said, like in a 10 megawatts power plant with a Kaplan runner that is located in Porjus and that belongs to the Porjus Foundation in Sweden also. And finally, the last test at the end of the project will be carried out in a very large Francis turbine power plant located in Oxla with 210 megawatts, and that is it's owned by Statkraft. In order to do this work, we have built a consortium that is formed by two universities, Universitat Politècnica de Catalunya and Lulea University of Technology, a small and medium-sized company, Flow Design Bureau, from Norway, the Porjus Foundation, which will provide access to the Porjus power plant, And then finally, two of the largest European renewable energy producers, which are Vattenfall from Sweden and Statkraft from Norway. And just to conclude, acknowledge the European Union's Horizon 2020 Research and Innovation Program, which is funding this project. Thank you very much for your attention.
Thank you, Xavier. The
Thank
last
you.
presentation is of the Hydroflex project. I give the word to you, Ole Gunnar Dahløg from NTNU Trondheim.
My name is Ole Gunnar Dahløg, and I'm the coordinator of the Hydroflex project. And I would first of all like to thank all of the presenters today. It was quite interesting to see. And it shows about what's going on in the hydropower business these days. Let me tell you a little bit about the Hydroflex project. I really would like to emphasize the question, the task we were given in the project. And that the task was actually to allow start-stop cycles to reach up to 30 times per day. And as I said, we haven't seen that kind of number of start-stops anytime. And when we run simulations with different scenarios, even the most optimistic scenario will not reach up to 30 times start-stops per day. But the whole point of the project is to evaluate or to develop a technology that can handle high flexibility for the European energy system and market in the future. The green hydro scenario gave up to 10 start-stops per day, but that was in extreme situations. What are we doing? First of all, it's meant to look into different technologies, and we are looking into turbine generators and transformers. And first of all, the turbine side of it is to look into how the question that comes up when you're doing these, when you're increasing the flexibility and you're increasing the number of start-stops of the turbine, you question the turbine lifetime. So you need to look into models of turbine lifetime. I think the most common question people come to me when we talk about this, the new flexibility market, is the remaining lifetime, or what does it actually cost to operate flexibility? What does it cost to the turbine? What kind of maintenance cost or reduced lifetime are we having? Those are the things we are looking into. So what we are addressing lifetime as a reduction by looking at the stresses in the turbine, and by doing model tests where we are addressing or measuring the stresses in the blades, we can calculate a reduced lifetime based on start-stops, high rampings, and these things. And the generator and the converter is also needed. We are utilizing variable speed operation in order to have less fatigue loads on the turbines. So what are the questions there? First of all, we need high power frequency converters, more than 100 megawatts, and of course, we need to have joint control of converter and rotor magnetization. These are tested in the Swedish center Porus, which was shown earlier by Xavier and from the AC4 Hydro project. So Vattenfall is also part of this project. And we need to mitigate the effect from high power electric converters, fast voltage switching. So these are the things we are developing, and new patents has already emerged, especially for the rotor magnetization project. We have to look at the environmental impact and its mitigations from this operation. Imagine having 30 start-stops in where the power or the water goes into a river downstream the power plant. Of course, that will have an impact. The question is how and why. So we are looking into we are questioning that things in downstream power plant in Sweden, in Umeå. And we are working on the social acceptance questions right now. The mitigation, though, is to try to dampen the large fluctuations of flow. So in the project, we have developed an air cushion underground reservoir system, kind of like a reservoir downstream that can dampen the high or the fast fluctuation in the river downstream the power plant. So there's an illustration of kind of a reservoir downstream the turbine, which handles the fluctuations. The question here is how to operate it in order to dampen the waves or large variations in the water or in the river downstream the power plant. So what kind of impact do we have from this? First of all, we are all of us talking about the hydropower system as an enabler of more renewables in the system. I think that's the mantra these days when it comes to hydropower. An enabler of more doing. We can reduce the maintenance cost and exceed the lifetime of the existing components and also in new components. And then we are looking at the increased turbine and generator performance. Lifetime environmental impact is also to strengthen the industrial technology base. And in the end, we will provide the knowledge on how to reduce the social barriers for flexible operation of hydropower plants. Thanks. That's what Hydroflex is about. Thanks for your attention.
Thank you very much, Ole. Now it only remains to thank you all for attending this EU Green Week partner event entitled European Hydropower is Important for the Green Deal. And I hope that this string of presentations have convinced you that this is really the fact. Thank you very much.